Hello. Okay. So good morning, everyone. Uh, let's start our class today. Okay. So at the beginning, I want to mention one thing that the project legacy Pi server in the requirement tool I've already uploaded in this week. Okay. I mean, week 13. You can download here, legacy Pi server. So this is related to the requirements tool here. Okay, here it asks you to do the Lexi Pi web service, right? So this one from here to here, and I've already provided you the Lexi Pi server here. Okay, this is the code for the Lexi Pi server, and please use the code I provided you. Okay, you don't need to create your own code for this Pi server, Lexi Pi server. Sorry. Okay, you have to use this one, the one that I provide you here. Okay. Okay, then let's talk about today's lecture. Here. So last week we finished web services and some more things about web service development, right? And today we are going to talk about something related to multiprocessing again. Okay, it's like we go back to the previous topic about multiprocessing. So there's some extra knowledge about that. Okay. So if you still remember that what I have mentioned yesterday, oh sorry, last week, that for your project for the students from course comp S 362, okay, 362, you need to write something about discussion of adopting advanced technologies, right? Okay, so this is like master queues, synchronizing programming, high performance computing. This is what we are going to talk about in this lecture and the lecture next week. Okay, because previously we've canceled a lecture, right? So we will have a makeup lecture next week. Okay, for the time I will provide you later. Okay, I will tell you about the time this week. And there, so the lecture next week, I mean, for the makeup lecture, and also we will have a makeup lab, okay, for next week. But both of them are not compulsory, okay? I mean, I will not take attendance for you. So if you have time, you can come, okay? But it's not um, compulsory. Yeah. And later I will message you the information about the makeup class in the WhatsApp group. Okay, and also in the email. Okay, then let's go ahead to the things today, message queues. So today we're going to talk about something related to inter-process communication, okay, which is called Okay, so we've already finished the cost evaluation, and let's go back to our lecture, okay? Yeah, so as I said, we are going to talk about the inter-process communication between processes, okay? This is called IPC. And there are two, actually, there's a typo here. We're not going to talk about 0MQ, okay? And yeah, so there are three main content today. Okay, IPC and messaging, and then how to program IPC pipes. Okay, those pipes are used for communication between different processes. And also we are going to talk about message queues. Okay, so firstly, let's talk about IPC. Okay, inter-process communication. So actually, I mean, there are different ways for concurrent units, right, of application to coordinate and communicate. So we know that for threads, it is created in the same process. So they have shared variables. Okay. And shared variables are only used for threads. So those shared variables are not interprocess. They are in the same process, right? And for processes, they don't have shared variables. So what we do is that we use, because they used independent resources. So how they communicate, as we've learned that we usually create some shared memory in the operating system for the process to communicate each other, right? So this is as what is written here. It is supported, this kind of sharing memory is supported by operating system. Okay, and actually we can also use like messaging, okay, like passing message for processes. Actually, we've already used it in our previous lectures or labs when we're talking about multi-process tasking. Okay, if you still remember that we've used some pipes actually for them to communicate with each other with the pipe. Okay, so but at that time we are talking about this code, but we didn't talk about the details of about how it works. Okay, so today we are going to talk about more details about inter-process communication. Okay, yeah. So firstly, let's talk about messaging. Okay, so we have two processes, and then we want to communicate with each other. So we need to transfer message to communicate between the processes or distributed system. This is called messaging. Okay, just like the words message, send message and receive message. Okay, so one process is going to send a message to another process, and another process is going to receive the message. Okay, so very simple. But this communication, okay, is mostly asynchronized. And I mean, of course, it can be synchronized, but most of them are asynchronized. Okay, so what means synchronized and asynchronized? So a synchronized mode, the sender doesn't wait for the receiver. Okay, so it's just like the sender send a message and it doesn't care if the receiver accept or not. Okay, so it's just like in the WhatsApp, right? Sometimes you pop up message in a group asking me about something related to the course. But after you send a message, you will not keep waiting for my uh, response, right? You will start to do other tasks by yourself. And then maybe I will reply after several hours, or sometimes I'm too busy, so I will reply the next day. Okay, so this is called a synchronized mode. Okay, so it means the sender doesn't wait. It will proceed other tasks after send the message. Okay, and then this message will be stored in the memory. Okay, and until the receiver accept the message. And then how about synchronized mode? So synchronized mode is just opposite to a synchronized mode. So it's very easy to understand. So every time the sender will wait the receiver to accept the message. So just like you are calling your friends, okay? So if your friend don't pick up, you keep calling him, right? So this is a kind of synchronized mode, okay? Okay, then let's talk about how to do IPC pipes programming. Okay, so firstly, this is the main concept, and then let's talk about programming. Okay. So we will use, in this case, we are going to use pipe. Okay. And a pipe is just like a master cube between two processes. And it is used for inter-process communication. And usually it is implemented in Unix-like and Windows operating systems. Okay. And in Python, we have some APIs for creating pipe between processes. Okay, so it's called os.pipe and multiprocessing.pipe. And this pipe can either be unidirectional or bidirectional. What means unidirectional? So unidirectional means the pipe, the direction of the message is defined, is fixed. Okay, you can only send from one side to another side. Okay, for example, it has side A and B. Okay, then A can only be the sender and then B can only be the receiver. Okay, so it's a unidirectional pipe. And sometimes the pipe can also be bidirectional. So the A and B can either be the sender or the receiver. Okay, so the direction is not defined. It is more flexible. And then let's see how to create a pipe. So we have this pipe method. Okay. And this pipe method will return a pair of connection object. So it's return a pair of connection object, okay? Representing the end, start and end of the pipe, okay? So if we look at some code here, it will be like this. So when we are using multiprocessing.pipe, okay, it returns you two ends. Okay, one is the start, another is the end. Okay, connection one and connection B. Okay, if we treat a pipe like this, okay, like a tube, then this will be okay, and this will be connection, sorry, connection one, this will be connection two. Okay, so it represents this is a pipe. Okay. And then this represents for the communication between two different processes. Okay, so this is two ends. Okay, and then because this is bidirectional, so the message can either send from connection 1 to connection 2 or connection 2 to connection 1. Okay, this is called bidirectional. Okay, because we're using multiprocessing.pipe. So as we said, when we're using multiprocessing.pipe, it's bidirectional. And then there are several methods in the connection. Okay, very simple. Send, receive, and close. Okay, send is to send the object to the other end of the connection. Receive is to return object sent from the other end of the connection. Okay, and close is just after we finish the communication, we close the connection. That's it. So let's look at some example here. Let's see, we have two processes. Okay, P1 process 1 and P2 process 2. So what it is doing here? It's very simple. Okay, so P1 is just going to send a message of hello, and then print the name, and the message is sent. After it sent a message, okay, it's also trying to receive message from another processes in this connection. And P2 is doing the same thing. Okay, after it receive hello, okay, it print the process name and some string of receive. Okay, and then it will also send a string of word, and then print the message it has sent. And then we have two processes, P1 and P2, right? P1 and P2. So we're just using multiprocessing.process, if you still remember, to start the processes, okay? And then for each processes, it will have a target function. Okay, so for P1 and P2 is a target function. And then process 1 will send a message hello at the beginning, right? As it is written here. And then after process 1 send a message, process 2 will print that it has received the message. Okay, and process 2 can also send a message, and then process 1 will also receive a message. Okay. So this is bidirectional. Process 1 can send message to process 2, and process 2 can also send a message to process 1. Okay. And then how do we send a sequence of values? Okay, or we say how we know the end of the string, the end of the message. So there are two approach. Okay, one is to use a sentinel. So this is called it's just like a stopping value. Okay, with some special value that will not be existing in the message. It's better to use some invalid data value like none. Okay. For example, you can use none. Or -1, something like this. Another approach is to close the connection after you finish the communication. Okay, close the connection. So why we need these two approach to end the communication? Let's have a look in example. Okay. So here we have a parent process and a child process. Okay, the parent process is just the main process of the program. And then what we need to do is just we need to create child process. Okay, so because the parent process is the main process, so it is existing once you run the program. Okay, so this is where you run the program. And then in your parent process, you can create child processes, if you still remember. Okay, we've talked about it in the previous lectures. So parent process can create child process. Okay, so what we're doing is we create child process here. Here. Okay, and the function in the child process is the one defined here. So basically, this child process is just used to receive message from the parent process, okay, with this connection dot receive. And then we need to write that if the object, the message that we receive is a sentinel, then we break, okay, and then we print the object. No. And if it is not sentinel, then we print the object, the message. Okay, and then the sentinel in this case, we are define it is as an invalid value of none. Okay, and then after that, in the main process, we create a pipe between these two process. Okay, child process and parent process with pipe. And then this pipe is used for sending and receiving message between these two processes. So in this case, parent is sending message of a random value between 1 to 100. Okay, and then we use dot send after we finish all the message that we want to send. We use sentinel in the parent process to finish the communication. Okay, and then this message, okay, is necessary. Okay, so because you may have questions that because here is a loop for 10 times, right? And after the loop, after they've sent message for 10 times, of course, it will not send message for any more, right? So why we still need to put a line to send a sentinel after we finish the loop? So the reason is that you need to tell the child process that you finish what you are going to send. So just like in our class, right? So if I stop talking for like 5 minutes, will you leave the classroom? I think most of you will stay in the classroom, right? If I stop talking for 5 minutes, because I didn't tell you any information about if this class is finished or not. So let's say I am the parent process and you are the child process. So only if you receive some message that I said that the class is over, then you'll get out of the class, right? Or you might stay here. So this is the same principle as the processes here. So every time, if the parent processes have finished what it want to send, it need to send a sentinel to the child process to inform the child processes that the message is finished. Okay. Or the child processes will hold the resources and keep waiting the message. Okay, so it will be a problem. Okay, that's it. So this is one way to send a sentinel, right? And another approach is to just to close the connection. So this is the first example for sending sentinel. And the second example is to use, this close method. Okay. So it's the same thing that after the child process have finished all the message it just closed the connection. So this is another way, okay, to end the communication. So I'm not going to talk about more details, right? So very simple. The only difference is just the last line of these two codes. One is used to send a sentinel, another is to close the connection directly. Okay. Then let's talk about some more complicated things. Okay, unidirectional pipes. So in the previous example, the pipe is bidirectional. So actually, there is not a lot of thing to define. Okay, so you can send message anyhow you want. Okay, and then if the pipes is unidirectional, you need to carefully design how the pipes is connected between the processes. Okay. So in these unidirectional pipes, the connection of the pipe are input and output. Okay, it can be input or output. So this input and output of the direction are considered from the processes, not from the pipes. Okay, this is a very important thing. Okay. So when we are talking about input and output, it is considered from the processes side, not from the pipe side. Okay. I think you might not understand this part now, but later when we are talking about the example, you have a deeper understanding. Okay. So it means input. So usually when we define the unidirectional pipe, okay. So if it is unidirectional, we need to put force here. Okay, it means the bidirectional is disabled. Okay, we need to put force here. And then it has two connections, right? One is input, one is output. Okay. And then output is used to send message. Okay. Input is used to receive message. Yeah. Then okay, doesn't matter. Let's look at some example. So here again, we have several processes. And then this time we are going to check if one number is divisible by 2 and 5 or not. Okay, so here is a function just to check if the number, if the message, the value can be divided by the number that you defined here. Okay, so a very simple program. Okay, if it can be divided by this number that we defined here, then we just send the message. Okay, if it is not divisible by the number that defined here, we will not send the message. Okay, so let's look at the main function. So here we've created 3 pipes. Okay, 3 pipes, 3 unidirectional pipes. And these 3 pipes, each of them has 2 ends. Okay, connection 1 input, connection 1 output, and also connection 2 input, output, and connection 3 input, output. And after the main process, we also define 2 child processes. Okay, so the child processes, we have a target function of divisible, the one we define here. Okay, to check if the number sent by the main process can be divisible by the number that you define here. Okay, so here the first process is used to check if the number can be divisible by 2. And the second process is checking if the number is divisible by 5. Okay, so what the process is doing is like, if the number sent from the main process is divisible by 2, then it will send this number to the next process. Okay, and then if again the filtered number, okay, is divisible by 5, and then the second child process will send this number back to the main process. Okay, so in the end, what we get is that all those numbers that is divisible by 10. Okay. Okay, so if the logic is like this, we send the main process, send the value of n, okay? And then process 1, check if this is divisible, okay? And then process 2, and then if it is divisible, then the number is sent to process 2. So firstly, the number is sent to process 1. And then if it is divisible by 2, then those number will again send to process 2 to check if this can be divisible by 5. Okay, and then if it's divisible by 5, it will return those number back to the main process. Okay, so this process 1 and 2 is just working like a filter, okay, to check if the numbers are divisible by 10. That's it. And then how we connect the pipes. Okay, this is the most important things. So we now know about the logic. Then how we define the pipes. Because if you look at the pipes we're using here, okay, so in process 1, so this is process 1, right? The connection we used is the input of connection 1 and output of connection 2. Okay, I think you might feel a bit confused. So if there's one tube, right? This is one tube. Okay, we have, so let's say this is CO connection 1, and connection 1 input, and the connection, connection 1 output. So what you think, okay, intuitively it should be like this. Okay, the process should be like this, process. Okay, this is process 1. And what do you think it should be like this, right? Process 1 gets the input from the connection 1. Okay, so this is the input from connection 1. And then send output to the here, right? So this is like intuitively, it should work like this. So like the process should be connected to the input and output of a tube, of a connection. But actually it is different, because we said here, input and output are considered from processes, okay, not from pipes. So we can have a look on the graph that I've demonstrated here, okay, to illustrate how the program work in this case. So we have the main process. This is the main process, okay? And then here is another process. This is process 1. This is process 1 to check if it is divisible by 2. Okay, and then this is process 2. Checking if the number is divisible by 5. Okay, and then we have 3 pipes. And these 3 pipes, we have input and output, right? Every time we define a pipe, we have input and output, okay? And then the main process is sending message to pipe 1, okay? But the end which accepts the message from the main process is the output of the C1, is C1 output. Okay, so this is the thing that you need to pay attention. That's what I said. Output, when we are talking about input and output, we are talking it from the process side. Okay, that's why the output, the name C1 output of a pipe is getting the output data from the previous process. Okay, and then the input of the pipe is used to input data to the next process. Okay, so that's what I mean, what is written here. The input and output are considered from the process side. Okay. Okay, and then the same idea for pipe 2, the result of process 1, okay, is output to pipe 2. Okay, and then the input of pipe 2 is inputting data to the next process, which is process 2. And then process 2 send data again to the output of pipe 3. And then the input of pipe 3 finally send message back to the main process. Okay, so then if you look at this graph, it will be very clear. So when you are defining a process like process 1, you need to connect it in this way, right? So you need to combine these 3 things together, which is C1 in and C2 out. Okay, that's why in this code, we are doing like this. Okay, the arguments of this function is C1 in and C2 out. So this is aligned with the graph here. Okay, and then for process 2, the 2 arguments of process 2 are like this: C2 in and C3 out, right? So what we are doing is here, C2 in and C3 out. And then in the end, in the main function, okay, we are getting the data, okay, from the result. But we get data from this connection 3 input, right? So this is also like what we defined here. The last end of the pipe 3, which is connection 3 input. Okay, so this connection 3 input data to the main process. Okay, and then the main process print out what it has received. Okay, that's it. So any questions here? This is how you construct the pipes with the processes, how you connect the different ends of pipes and the processes. Okay. And actually, I've also written here about the procedure of the connection of pipes. Okay. So this is equivalent to the graph here. But I think the graph is more clear about how the processes is connected to the ends of different pipes. Okay. Okay, then let's have a break of 10 minutes and then we will get back at 10 o'clock. Okay. Okay, so let's go back to the class, okay? Okay, so now we are going to talk about second part of this unit 11. Okay, master queues. And talking about master queues, we need to first know one thing, which is called MOM, message oriented middleware. Okay. So what is the middleware? Okay. Middleware. Okay, message oriented middleware. Okay. So what is a middleware? Middleware is usually a kind of service between different applications or between software and your operating systems. Okay, it provides you the communication between your software and operating system or between different applications. Okay, so this kind of services or program is called middleware. Okay. And then message queue is based on message-oriented middleware. Okay. And then it's kind of application server supports sending and receiving message. Okay. Just a service to send and receive message. And then this kind of middleware have three main features, which are asynchronicity, routing, and transformation. Okay, what means asynchronicity? So this is mean asynchronized, right? This is what we talked just like a few minutes ago. And in this case, it just means the middleware in the communication will persist a message until a client receives it later. Okay, and then look at this sentence. You might feel a bit different. Oh, it's a kind of different idea. Was if we talked that at the beginning that in the asynchronized mode, the sender doesn't wait for the receiver, right? Here we said that sender doesn't wait for the receiver. And then here we say that it persists a message until a client receives it later. Okay. So what means persist a message? Here, when we see persist a message, it doesn't mean the sender is keeping sending the message until the client receive it. Okay. It means this message, after the sender dropped the message into the middleware, the sender will just leave. Okay. And the sender will keep doing his own other tasks. Okay. And then this message will be persistent in the middleware, and it will be stored in some hard disks or memories. Okay. That's why we say this message is persistent. So in this way, if the system corrupt or if you restart the whole system, this information will not be lost. Okay. And this is the advantage of MOM. Okay. Asynchronicity. And then the second feature is routine. So in MOM, so you can customize how you want to send a message. So you can send a message to a single client, or you can send message to multiple receivers. Okay, so this is, you can customize to which receiver you want to send a message according to the types of the content. Okay, and then you can define whom to send by yourself. And then the third feature is called transformation. Okay, so very easy to understand. So the message format is not fixed. So you know, like between different sender and the receivers, they might use different format of data, right? So we can convert Python data to JSON data or JSON data to Python data. So this is like the message format sometimes is different. Okay, but MOM, it can modify the message format and the content, okay, according to the requirements. So you can understand these three features as the three advantage of message queue. Okay, and then in your discussion, in your project, for students from 362, you can also talk about the three features in your project about how message queue benefit your application. Okay. And then based on this MOM, message queue is a first in, first out FIFO buffer. Okay. What means first in, first out? I think you know about that, right? So let's say we have a buffer here. Okay, and then we are sending message into the buffer. So we have like 1, 2, 3, 4, 5, in total 6 message. Okay. So this is the first message that you receive put in the buffer. Then the second one, third one, fourth one, fifth one, sixth one. Okay, so when the when the receiver, okay, is going to get the data from the buffer, it will get the first data first, and then second data, okay, according to this order of input. So this is called first in, first out. If the data arrive first, then it will go out first. So this is called FIFO buffer. Okay, and this buffer in master queue is used for communicating data between different processes. Okay. And actually, most people use message queues to refer to messaging in general. Okay, so anytime we're talking about messaging between processes, we in practice we can say this is a message queue. Okay, and then there are two common messaging model, obviously messaging pattern. Okay, one is point-to-point messaging, another is publish and subscribe messaging. Okay, this is two common type for message queue. So let's first talk about the point-to-point messaging. Okay, so very easy to understand. Very easy to understand. So the sender places a message on a queue with optional expiry, and then the receiver obtain the message from the queue. Okay, so it's point to point. So there will be only one sender and one receiver. I mean, there might be some alternative receivers, but for each message, only one receiver can get it. Okay, so this is called point to point. So the sender put the message inside this queue, and then the receiver who needs this message will take the message, and others will not deal with this message. Okay, so only one sender, and then only one receiver will receive the message. So it's just like what I've written here. One receiver obtain the message from the queue, and after the receiver obtain the message, this message will be removed from the queue. Okay, which means only this receiver can obtain the message. Other receiver will not able to receive this message anymore. Okay, and here it gives you example like online e-commerce order processing. So every time you buy something, okay, you put an order in the website, and then someone will fetch the order, okay, and process the order, right? And then after someone process your order will be disappeared, right? The state will change. Okay, so it will disappear from your order that hasn't been processed yet. So this avoid that some other worker to process it again. Okay, so because you only put one order, so your order should only be processed for one time. If it has been processed for 2 times, then you'll get double things, right? So that will be a problem. And you also need to pay twice. Okay. So usually in the e-commerce ordering system, it is based on point-to-point messaging. Okay. And then here's another messaging model called publish and subscribe messaging. And this is main difference is that in this model, you can have multiple users, okay, or you can have multiple receivers, okay, to receive the data, just like multiple users subscribe a topic. So when the publisher, in this case, the sender is called the publisher, okay. If it posts a message, this will be visible to all the subscribers. So it's just like when you send a message in the WhatsApp group, okay, the message will be visible for all the subscribers. So all the subscriber will get a message and process the message. Okay, so this like one to multiple, okay, not point to point. Okay, and then one advantage for this publish and subscribe messaging is that the system may be set up to send a message to a previous offline. Here's a typo, offline. Okay, offline subscriber. Okay, so even you're offline, you will get, when you are online, you will see the message, right? Because this message is stored in the memory, in the hard disk. Okay, even your system restarts or corrupt, the message is still here. Every time you go into your WhatsApp, you will see the message. Okay, it will not be deleted. So this is called publish and subscribe messaging. Okay, then it's the end of this unit. Okay, we only talked a little bit about message queues and IPC. Then let's talk about the next one, Unit 12. Okay, the second part of this class. Okay, asynchronous programming. So we've talked about synchronizing for many times in the previous unit. Okay, so now we are going to talk about asynchronous programming. Asynchronous programming, okay? There are 4 parts in this unit, okay? So firstly, we are going to talk about the basic concept of asynchronous programming and what is coroutines. And then we are going to talk about Python generator, okay, which supports asynchronous programming. And then, okay, in this lecture, we are going to talk about these 2 parts. Okay, and then in the next makeup class, we are going to talk about these 2 parts: Python asynchronous basics, asynchronous IO basics, okay, and networking. And in the makeup class, we are going to talk about Unit 13, okay. Yeah, that's it. So let's talk about the first 2 content here. Okay. And so what means asynchronous programming? Okay. So it just means, refers to sending code to run outside the current flow of execution and continue without waiting for the code to complete running. Okay, let's have a look at the diagram here. Okay, like in the normal Python, or we say general, it's better to say general, okay? General Python functions. Okay, when we are doing this main function, let's say this main function we defined as caller. Okay, and in this main function, we'll call some other functions, right? I mean, the main program, we might call some other functions in the program. So this function that is called by the main program is called the subroutine. And every time if you call a function, it will execute the whole function. And then after it finished the function, it will return the result to the main program, obviously to the caller. Okay. So this is called a subroutine. Subroutine. Okay. With subfunctions inside your program. And in asynchronous programming, we are using coroutine. And a coroutine is a generalized subroutine that allows execution to be suspended and resumed. Okay, so let's look at this program here. So still we have a main program. We call it caller. Okay, and then we call another function that we defined. Okay, so that function is called a coroutine. Okay, actually, just the difference in name. Okay, here we can say another. Okay, the name is different, but it's just like another function. Okay, so this is a function you define. You can treat it. You can regard this as another subfunction. Okay, and the difference is that we can call this function, and on the half of the way of executing this function, we can go back to the main thread. Okay, and then after some time, you can go to this function again to continue this coroutine in this subfunction, and then finish the rest work, and then go back again. Okay, so it means for the coroutine, the main thread can access to the coroutine for many times, and then resume the main thread or the main program at some time that you defined once you met a keyword called yield. Okay, it go back to the main thread, a main program. And then once you see the keyword of next, you go back to the coroutine. Okay, so it's a kind of interleaved way, right? Very similar to multi-thread tasking. Okay. So here are some concepts of it. Okay. So it is supported by different asynchronous programming can be supported by different mechanisms. Okay. So we are talking about coroutine in this class. Okay. And then later, I mean, we are going to talk about this building model of asynchronous I/O. Okay. So here I've just explained about the difference between subroutine and coroutine. Okay. And then if you still remember about this table, actually this table I've showed you at the beginning of this course. Okay. I think it's in the first or second lecture. So we have several concurrent solutions in Python, right? One is processes, one is thread, another. So these two we've talked about it at the beginning, and another thing is called asynchronous I/O. Okay, so they are based on in Python. They are based on different modules, right? So these modules are at least here, and the concurrency types for processes, as we said, it is real parallelism, right? And then for threads, multi-thread tasking, it's preemptive multitasking. Okay. And for asynchronous programming, it's called cooperative multitasking. We'll see the difference later in the code, okay? And then for processing, we need multiple CPUs, but for thread and asynchronous programming, we only need one CPU. And then, as we said, in multi-processing tasks, it's suitable for CPU-bound tasks. And for the other two options, it is more suitable for IO-bound tasks. This is just because of Python, okay? If you still remember that we have something called Python GIL, right? GIL, Python GIL. So this limited that the multi-thread tasking to be used in CPU-bound tasks. Okay. Okay, here is an example. We are going to compare the three kind of concurrency solution. So we have a function. Okay, this function is just to use to log the concurrent unit and the number of the this number of the this number of the time of this task is doing. Okay. Yeah. So n is the this 2 is the concurrent unit. So in this example, for each solution, we are going to have 2 concurrent unit. Okay, and we are going to run the things for 3 times. Okay. So let's see. So the first function is a log function, logging function. Okay, it will just give you 2 things. Okay, 2 things that you are going to show here. One is the process name, another is the thread name. Okay, these are only 2 things. And then it will show you the unit ID and the processing the number. Okay. So we are going to do a very simple task, counting. Okay, from counting in a number of range n. Okay, that's it. We're going to counting number with a processing time of 0.1 second. Okay. So this sleep time is just used to simulate the time for processing. And then we have several functions here. The first one is based on process. Okay. So the target function is the counter, and then the arguments is the number of the concurrent unit, and then we just start the processes. Okay. And then for the threads, it's the same. Okay, for thread, it's the same. We have the target function of the counter. Okay, and then the only different thing compared with the previous lectures is that we add one solution of asynchronous programming. Okay, so we use a co-counter. Okay. And then we use some keyword of await. Okay, a synchronized wait. But we haven't talked about these things yet. So I'm not going to talk about detail of the code here. Okay, so this explanation of the code we are going to talk about later. Okay, after we introduce the asynchronous IO lab library. Okay, asynchronous IO library. So here we are just going to compare the difference about these 3 solutions. Okay, so you don't need to think about the details of how these asynchronous programming work here. Okay, so you just need to know that we do this task of counting based on 3 different solutions: process, threads, and coroutines. And then let's see the result. So we have run this task for 6 times. Okay, we have 2 concurrent unit, and each unit has been run by 3 times. So that's why we have 6 messages for each solution. And then we can see for multiprocessing tasks, we have different process. Okay, we have process 1, process 2. So this is the concurrent unit for each task. Okay, and for each process, we only have 1 thread, the main thread. Right? So this is for processes. And then for threads, the difference is that we all use the same process, which is the main process. And in the main process, we will have different thread 1 and thread 2. Okay, for multiple times. And then, so this is what we've already talked about in the previous lectures. And then let's look at asynchronous programming. Okay, we have only 1 process, which is the main process. And also we only have 1 thread, which is the main thread. Okay. And this time the concurrent unit here is, you can see the ID is different, but they are using the same process and the same thread. Okay, so the concurrent thing here is just the coroutines that you defined here. Okay, so this is what we're talking about here. So it is using the same process, the same threads. The only difference is that it can switch from different tasks, okay, inside the same threads. Okay, between the coroutine and the caller. Then to realize these things, okay, usually we use Python generators. Okay, and a generator is just a simplified coroutine for generating values. And as we said, generator or this asynchronous programming, actually it doesn't support real concurrency. Okay. And it can maintain some internal states. So how we define a generator function? So actually the generator function is almost looks the same as a general function. The only difference is that we use a yield keyword inside the function body. Okay, so what we've talked about in the previous diagram. So we have a keyword of yield. And correspondingly, sometimes we will have a keyword of next in the main in the main program. Okay. So when we use yield in the coroutine or in the generator, so we usually do like this: yield x. So this is x is the result that you get from the coroutine. And when we are using yield x, then it passes this value x to the caller. And after it passed this value to the caller, your subfunction or your coroutine will pause execution. Okay, the execution of your coroutine will be stopped, or it's better to say pauses. Okay, will be paused. So it will stop this execution for a while. Okay, and after the caller call this function again, it will keep execute again. Okay, So when we call a generator function, it returns a generator object. Okay, this we'll talk about it in the code. And then when you call the generator function, actually the code inside the function is not yet executed. Okay, so this is an important thing. So when you call the generator function, the code is not executed yet. And then we have a keyword of next in the previous diagram, right? So this next will be put in the main program. And then every time in the main program you see this keyword next, it will go back to the coroutine and then obtain the next value from the generator. Okay. Then let's look at some example. So yeah, this is a very simple function, generator. Just like the original function, just like for n times, we print that this generator generates a value of I. Okay. And then the only difference is that we put a keyword of yield I. And then in the main function, firstly, we get this generator object. Okay, but as we said, when we call this generator function, yeah, when we call this generator function, the code inside this function is not yet executed. Okay, so when you call the function here, the code is not executed yet. Then, okay, we print this caller creates get object. Then we execute the code inside. Okay. And so the first message will be like this. Generator generates 0, caller gets 0. Because it's from 0 to n, right? And n we put here is 3. Okay. So for I in range 3, we'll run for 3 times. 0, 1, and 2. And then after we yield, okay, I from this coroutine, we use this keyword of next to go back to the coroutine. Okay, and then we print what the caller get from the coroutine, which is n. Okay, so I think this example is actually not very clear to illustrate the use of generator. Okay, let's look at some example later. Okay, so usually in our case, usually the next keyword is not used very often. Okay, so usually we use a list to replace this next. Okay, so for generator, usually we use it in a for loop, and then we obtain the values one by one, and then we convert to a list. Okay, we obtain the generator value at once. Okay, so and then with this list, we do this coroutine. Okay, we will talk about, you'll understand it later in this example. Okay, let's have a look at this example. So again, we are using the same code. Okay, Uh, wait. Let me talk about this first. So let's compare. Let's compare one thing. Okay. So to illustrate this, the use of generator more clear. Clearer. So if we delete this yield here, okay, and let's see, we also delete this next here. Then this code went back to its original version that you are very familiar with subroutines without coroutines. So just like in the get numbers in the for loops, it prints all the things, okay, for from 0 to 2, okay, and then in the caller, it also print the values of 0, 1, 2 for 3 times, right? So what's the difference? Okay, so the difference is that the result will be like this. So at the beginning, you will use this generate number function, right? This generate number function. So then the generator will first generate 0, 1, and 2. Okay, these 3 numbers will be generated together. And then your main function, it will generate also 0, 1, 2. Okay. So it will be like this. This generator, generate 0, these 3 strings will be printed together first. And after that, you will print these 3 strings, okay, which is in the main program. Okay. So this is in the subroutine way. But if we use this yield, if we use this yield, okay, so we just clean all the things. Now we add 2 things. Which is yield and next. Okay, so although it is still in the loop, okay, but if the loop meets the keyword of yield, the loop will be paused. Okay, it will be stopped for a while. And then it will go back to the loop in the main function. Okay, and then print this one. And after the main function print this caller gets, okay, then in the next loop, it will use this next keyword to go back to the loop here. Okay, and then it just continue doing the same thing. Print the generator generates something, and then it's yield back to the main loop here. Okay, so then this program work in an interleaved way. Okay, this is the difference when we are using yield compared with subroutine. Okay, difference between coroutine and subroutine. And then let's replace it by list. Okay, so this function here is kept the same. We don't need to change anything. The only thing that we need to change is here. For n in generator numbers, okay, so here generator numbers, this function will give you a list of the number inside. Okay, so then we will get n from the generators and then print n. Okay, so this is the difference. So in this generator, it will has the same I mean, this will be equivalent according to the previous code when you are using next. Okay, so every time when you meet this yield, okay, this function will be paused and then go back to the function here to print the caller gets in. Okay, that's it. So here we replace this next. Okay, we replace this next with a list based on these two lines. Okay. And also after that, we also use this line to get the list to print it out. So actually it's doing like this. So we create a list of 0 and 2. Okay, and then in the every time when the generator generates a number, print it out, and then it will get the caller also will get one number from the list. Okay, and then in the second iteration, it will get the second element in the list, and also the next one, it will get the last element in the list. Okay, so this is how we replace the next keyword with a list. Okay, then let's look at some other examples. Here is the example of Fibonacci series. What is a Fibonacci series? So it just means the next number, okay, is equal to the summation of the previous two numbers. So let's say the number 3 here is equal to the summation of 1 and 2. And then this number 5 is equal to the summation of 2 and 3. So this is called Fibonacci series. Okay, and then in this Fibonacci series, here we're trying to use coroutine to solve this Fibonacci series, okay, to print the Fibonacci series. So what it is doing here is that at the beginning, we define the first two number in the Fibonacci series as F0 and F1, which is 0 and 1. Okay, and then in the loop, we will first get the value of F0, go back to the main program. Okay, and then in the main program, it will print the index and also the value of the F0. Okay. And then it will print for 10 times. So let's see, at the beginning, F0 is 0. So when it goes to the loop, it meets the keyword of yield. So it will send the F0 to the main program. So the main program will print F0, which is 0. Okay, and the index is also 0. So this is the first thing that it print. Okay, and after that, it will go back to the Fibonacci function. Okay, and then it will keep doing this loop again and again. So the second time, F0 became F1. Okay, and F1 became F0 plus 1. So that's why the second time F0 is 1. Okay, and then you will send again this new F0 to the main program, and the main program will calculate as like this. We'll print like this. The index is 1 and the F0 is equal to 1. Okay. And then the next time, F0, this time F1 become F0 plus 1. So F1 is 1, F0 is also 1. Okay, so the next time F0 is still 1. But F1 become 2, right? So the next time you put the F1, you give the value of F1 to F0, and then F0 become 2. So you print it out again. So it's like this is the principle of how this Fibonacci series work with the coroutine. Okay, so the main point is that you need to know when this value is sent to the main function and print out. Okay, so this is the main point. So when you are designing this coroutine, you need to know where you need to put this keyword of yield. That's it. And yeah, here are some other generator, but I think almost the same. So we're not talking about it. Okay. I think it's almost the time. So, okay, so it's the end of this course. I mean, this class. And yeah, see you later in the lab or tomorrow. Okay. Thank you very much. Mm, sure. Yeah, so as I said, we will have a makeup class and makeup lab, makeup lecture and makeup lab next week. Okay. But as I said, there'll be no attendance. So you can come or either come or watch the recording. Okay, doesn't matter. Because I think the makeup class might not be on Monday morning. Okay, so we need to check the availability of the classrooms. So that might have some clash with your schedule. So if you don't have time, you don't need to come. You can watch the recording if you want. Okay, that's it. Okay, see you later.